All right, so I'm Matt Koslovsky. I'm a biostatistician for KBRWylie, and today I'll be talking about immersive data analysis for NASA biomedical data. All right, so this is a high-level synopsis of the stages of research, which I've categorized into 4 steps of planning, data management, analysis, and dissemination. So first in the planning stage, we're focused on the design of our study, how to allocate resources of time, money, and personnel, determining how and where the data is stored, as well as who is going to have access to the data, and getting IRB approvals. Then in the data management step, data are collected, cleaned, and processed before analysis. In the analysis step, we're focused on developing and applying visualizations and analytical methods, as well as processing and interpreting our results. So lastly, the results are disseminated through presentations, publications, and decision-making tools, as well as through the media. So here I've kind of highlighted the components that are directly involved in the data analysis. So software companies are constantly trying to integrate all these different components to streamline their functionality within the analytical environment. So historically, it's quite common, if not mandatory, for these software companies to integrate the data management and the analysis components into their software. However, more recently, I find that companies have started to integrate more of the planning and dissemination tools into their softwares. I think for the latter, this is most evident with software's ability to do dynamic predictions, or presentations, excuse me. For example, with Shiny Apps in R, or dashboards in Tableau. So why have software companies been integrating all these components? Well, first off, it's really required by the analysts to be able to perform their jobs. We don't want to be jumping around 5 different programs to perform one analysis, though sometimes this is necessary. We want to be able to clean and organize our data, produce the visualizations, perform the analysis, and do our presentations, oftentimes dynamically, all within one environment. This software integration provides more access to the data itself, tools built for the analysis, as well as the insights, all within an interactive and collaborative environments. As a result, this software integration augments various aspects of the data analysis process. This optimizes research as it's more efficient, it produces less errors, the results are reproducible, and lastly, it increases the level of inference drawn from our data. So for a moment, let's focus here on this last bullet. Does increasing the level of inference drawn from the data purely sound like a benefit of software integration or a research aim in itself? So here's an example of a recent project we've been working on at NASA to extract more of the information from the NASA biomedical data. So the aim of this study was to generate hypotheses regarding physiological changes associated with spaceflight exposure to identify anomalies and trends across data sets collected during research and operational studies, as well as during clinical care visits. So the approach that we took was to develop a network-based clustering algorithm for multivariate repeated measures data. It's a 3-step approach which takes advantage of previously developed machine learning and statistical methods, for example, clustering and community detection algorithms, as well as your traditional network analysis methods. The approach that we developed is highly visual, which aids in the synthesis of the high-dimensional data. And as a result of all of these components, our method can cluster discrete and/or continuous data. It can be specified to not require any strict assumptions. And it can also accommodate unequally spaced and unbalanced data, missing data, as well as data on different time scales. So we've designed a Shiny app in R for this clustering algorithm to support the integrated data analysis and presentation. So this is what the Shiny app that we've developed looks like. So briefly, this is what's happening underneath the hood in our 3-step approach that generates the network that you see here. So in step 1, we perform the univariate clustering for each of the repeated measure variables using any available method. In step 2, we build a network that connects individuals or nodes that are clustered into the same group for each variable. So if there are 3 measures that were repeatedly taken on a bunch of subjects, for example, heart rate, systolic blood pressure, or diastolic blood pressure, then there's going to be at most 3 edges between each node. And then lastly, in step 3, we identify communities in the network using any community detection algorithm. So in the Shiny app that we developed for this analysis, we're able to import any multivariate longitudinal data set. In this dropdown, we can choose which univariate clustering algorithm to use. Our approach is flexible in the sense that it can use any clustering algorithm, for example, k-means longitudinal. And we've built a few of them into the app already. Also, our approach is flexible to any community detection algorithm. So here the user can select from a few options that are available in the iGraph package in R. In this dropdown, the user can choose which variables to build the network on. So all of the available column names in the data set that was selected are populated into this and provided as options. The user can choose how to color the individual nodes within the network. So it's currently based off of the community assignment, but it can be colored based off of any of the attributable data or any of the attributes contained within the data set. With these drop-down windows, the user can select 2 of the different communities and do comparisons between them, for example, on their age, their gender, or disease prevalence. We can hover over nodes and see their individual attributes. And additionally, the user can select any of the univariate measures and have them plotted versus time. And by clicking on, any one of the individual trajectories within this plot, it'll automatically link to the particular node that it's associated to in the network, which helps look for patterns in the data. So while the analytical environment developed for the clustering algorithm is beneficial for accessing the data and exploring patterns in the data, as well as presenting results, there are various limitations of this app. First off, it doesn't really scale well. It works well for the small sample sizes that we have at NASA, but it's really difficult to visualize large networks and data sets. Additionally, we can't display multiple networks at once and simultaneously perform analysis on them. Second, do we really have an interactive environment when all we can do is point and click or hover on each individual node to see information about the underlying data? And lastly, what can we really visualize here? The company IASD has claimed that data has shape and that their shape have meaning. However, on a 2-dimensional screen, can we really fully grasp the shape of our data? So how can we remove these limitations and get more out of our data? So we propose integrating R and a video gaming software unity to render immersive data analysis and virtual reality that supports the data visualization, analysis, and presentation all inside of a collaborative environment. So what would an environment like this look like, and what barriers in the data analysis would this help alleviate? So here's an example of what that transition from a 2-dimensional network output to a 3-dimensional output would look like in virtual reality. So here we can see multiple analysts inside the virtual reality environment mining the data. In this setting, we are no longer simply visualizing the 3-dimensional objects in a 2-dimensional space. We're able to physically interact with our data. Users can interact with the data by moving nodes, but they can also move around the space to generate new insights. By selecting a node, they can generate pop-out windows to access even more data and analytical tools. In short, they have all of the capabilities of the Shiny app that we've developed, but inside of a fully immersive environment. So what else can we do in this environment? Here we can see that the analysts simultaneously investigating and comparing multiple different networks. While we don't show it, the graphical capabilities of Unity support animation of the data, and additionally, the space that they are standing in is limitless, so no data set is too large to visualize. Also, this virtual reality environment can seamlessly turn into a presentation mode as onlookers plug in from their individual laptops or computers or smartphones or jump into the virtual reality environment themselves. So there are numerous ways in which the virtual reality can enhance their data analytics. In addition to the ones previously mentioned, it also provides a collaborative environment that will allow clinicians, researchers, and other subject matter experts to step into the analytics environment together and generate new insights. The This interface can support various gestures from multiple users, replacing point and click and passing the mouse back and forth. The entire body can interact in the environment as both hands have controllers, and users can move around the three-dimensional space. Additionally, being able to view multiple network instances as well as the ability to record an analysis allows viewers to archive and review the progression of their data analysis. So we conjecture that this immersive data analysis in virtual reality will generate new insights for the NASA biomedical data, and as a result, we may be able to extract more information and value from the data that traditional methods may have left behind. It may help us better understand the links between sparse data sets from various sources, produce new ideas for data analysis methods for biomedical data, and lastly, set a higher standard for dynamic analyses and presentations. So in future, my colleagues and I are going to continue developing the VR environment for network analysis and eventually start applying it to other data sets. However, in part, this presentation was an exercise in what-ifs. So I'd like to leave you with a few more. So what if the R and Unity VR environment was developed for other analyses, such as heat maps, topological data, spatial data, or medical imagery? What if the VR environment was representative of data collection, storage, and access? What would that look like, and how would this help managers and stakeholders visualize the large-scale workflows across multiple sites or research groups? And lastly, what if it was used to display near real-time data summaries on monitored systems rendered in 3D? How would this help us understand the relations between the human system and the engineered systems that it interacts with, such as the International Space Station? Thank you.
We have time for questions. Does anybody have a question?
Hi, great talk. Question, have y'all deployed this to like production where your analysts can use it? And if you have, what was their reaction to this new kind of interface?
So we have the environment developed for within R, right, and with the Shiny app. And we've been playing around on a couple data sets. Our group doesn't necessarily need production. There's all of 5 of us. So it's easy to just kind of pass it back and forth. However, the virtual reality part of it is more of an idea than a product at this point. And so it's something that we're pursuing and we're looking for collaboration on. Thank you.
Hi, good talk. It was really interesting. I'm wondering if you've thought at all about how these types of platforms might translate into people sort of snooping the data until they find what they're looking for, especially those who don't necessarily have statistical backgrounds. And I'm wondering if you're thinking if what you've thought about to maybe mitigate some of that.
I mean, it's something that we face with any analytical method, right? It's not like developing a package for this is going to put it into a different set of hands that any other package wouldn't have access to, right? People just have access to those kind of things. I don't know how to prevent that. I think that as statisticians and as biostatisticians and as mathematicians, we need to be actively, I guess, just characterizing the kind of problems that can happen, you know, in the when these type of tools are put into untrained hands. But I don't know if I could be like the statistics police, you know, going around and preventing anybody from doing stuff. But it's for exploratory data analysis, right? So this is hypothesis generating. We're not going through and testing any hypotheses. So it's not like we're telling people to take the insights that they find and go and start presenting them as this is fact. It's to take them to that another intermediate step of study design and putting it together to do this type of analyses.
Yeah, I think that's a great piece that definitely will need to be emphasized.
Yeah, for sure.
People. Thank you.
Thank you for pointing that out. I think that's a really good point.
Other questions? Someone hand that down.
So you said your 3D was basically kind of a thought concept right now, and
Yes,
you're
sir.
moving towards developing that perhaps with some support But is there any reason why you linked it to R, or is the thought that it could be developed independent of the platform with just some sort of open API that could be called by any programming language?
Yeah, I mean, we've certainly talked about stuff like that. I mean, we're still trying to figure it out for just within R. We're just using this particular algorithm, particular method, particular setup to kind of showcase the idea and move it forward. But I think ideally the entire thing should be agnostic to the softwares, to the methods, to whatever. It's just not at that stage. But that's certainly in the thought process with the development.
Time for one last question. Anybody else?
That was a great talk, by the way. The only question I have is that what challenge do you face while developing or researching and develop these?
As far as just geared to the virtual reality aspect of it,
Everything. I mean, from forming the idea to research and develop and
okay, wow. You got another 15 minutes? I would say from conception, this problem came about based off of the needs that our customer NASA was looking for, right? We have a bunch of different data sets across a bunch of different sources. We have tons of longitudinal data collected on all sorts of different timescales, from within a mission to within a session to across the lifetime, right? Because astronauts are followed. Data collected on astronauts from before they even go up into space to way past retirement. So it's how can we put all this data together and synthesize it together? I think that's a common problem across research fields. So that's where it spurred from. We wanted it to be visual because we think that when you're working with advanced analytics, right, making things visual makes it easy to talk about, to do presentations on, to develop that inference. As far as from a developmental standpoint, I think R and Shiny is great because it's open source, and it's been really easy, at least to put together the app for us to be able to use it in-house. Taking things forward into the development of the virtual reality environment, I would say our greatest limitation at this point would be resources internally and externally. Potentially this would help us find a collaboration, someone that would show interest in something like this. But I mean, that's kind of where we're at as far as the development goes, unfortunately. So, did I answer your question? I know it's kind of multifaceted. Okay.
Thank you very much. Let's thank our speaker.